Alright, good morning everybody. In this video, we're going to start going over the lenses labs and maybe do one of the homework problems. I guess I should rephrase. In these videos, what I'm going to do is I'm going to break these ones into shorter videos. I've been trying to do one to get through all the labs, and then we'll get through some homework problems. And just having a lot of issues because I have to tab through a bunch of screens. So I'm going to do one thing at a time. We're going to start with the lenses labs. So if you have your optics lenses short labs, first one is about Snell's law. There are 3 options for which simulator can use. They are all basically the same. I just went with the bending light 1.1.20. It's the FET. I'm most familiar with FET. We're going to use the intro lab, bending light intro. And when you come here, I have a laser with a on-off switch, the red button. And then over here, I have controls to change the material. So right now I have air. So the white screen up here is all air, and then water. The blue screen down here is water. And if I look here on the drop-down menu, or in this case pop-up menu, there are other options. I have air, water, glass, mystery A, mystery B, and custom. I can just change the index of refraction to be whatever I want and see how it works. So for this lab, what we're trying to do is I want to see how the light, in this case a laser, behaves as it's changing through materials. So the first one I want to do is air into water. I have air and I have water. And it gives me the index of refraction right here. So index of refraction is it's a property of the material. Okay, so if I have air, the index of refraction is going to be 1. And I can use that knowledge to help me calculate things like the angle that the light is going to bend at. But in the case of this lab, I don't have to do any of the calculations. I'm just going to observe and write things down. So the N, index of refraction for air, is 1. So here I would type in 1.00. And then the index of refraction for water, our second material, is 1.33. So that would go here. I'm going to type those in, 1.00 and 1.33. All right, so now I want to measure the actual angle. Well, to do that, I'm going to use the protractor. It's really important that you get this lined up as best you can, right on the normal line here, where normal means perpendicular. So this line is perpendicular to our surface where the materials meet. So I put that dash mark right there, and I try to get the line across here going right on the horizon. So I want my 90s, my 90-degree angles, to be as close as possible right on the area where they intersect. Okay, then it doesn't matter what angle I have the laser at, but I'm just going to leave it where it is and turn it on. Okay, so for the air, my light is coming in at an angle of 10, 20, 30, 40. It's right between 40 and 50. I'm going to call it 45. So 45 degrees. And then the angle that it refracts at through our water is right down here. Now, this is really important that you have to be very precise on your measurements if you want the math to work out later. All right, so 10, 20, it's a little bit past 30. I'm going to say 32 because it's closer to the middle than it is to 30. So it's not quite 33, it's a little past 31, so I'm going to go with 32. Now, I'll show you why that's important. Using this right here, Snell's law. So with Snell's law, N1 times the sine of theta 1 has to equal, let's leave it at that, N2 times the sine of theta 2. So our N1 for air was 1, and our angle was 45. So if we punch that in our calculator, 1 times the sine of 45 degrees, we get 0.707. So that has to be equal to what's happening with the light in the air. So our N2 was 1.33 times the sine of our angle, theta 2. Now, if I just rounded it and said, oh, I'm going to call theta 30. It's close enough, right? Well, if I do 1.33 times the sine of 30 degrees, I get 0.665. Those are not equal. Now, if I go with theta equals 32, with our better estimate, 1.33 times the sine of 32 degrees, I get 0.705, which is much closer. And then the same thing if we round up too far on the other side, even if I go with 33. So 1.33 times the sine of 33, I get 0.724. Okay, which again does not equal. Okay, so it's really important that we're measuring these angles as precisely as possible to make sure we're getting the right work here. Okay, so then you would do the same thing here. We're going to switch water on the top. So the drop down, go to water, and switch to glass on the bottom. So we have some big glass platform, or say like it's our fish tank, and this is the tank, and here's the water in the tank. And we shoot a laser. We want to see what happens. So for this one, as you move it, or any of them, as you move it, there we go. As you move the angle, let's go with 30. The steps are the same. So the index of refraction is 1.33. Our angle coming in is at 30. Our index of refraction here is 1.50. And then we would measure our angle again being as precise as possible. Now for this second part, does it bend towards or away from the normal? So as I move, like wherever it is, let's go with that first one. It's easier to see. Air into water. We were at 45. Okay, so it's coming in here, and now if it wasn't bending at all, it would just go straight through, back out at 45. Right, so that's where the light should continue going, but it's hitting a different material. Now what we want to know is, does it bend towards the normal, which is the perpendicular line, or is it bending away from the normal, back towards 90 degrees? Well, in this case, the angle is less than 45, so it's bending back towards the normal. So here we would just highlight or select for that. You can just go like this, and then you can just highlight it. That works. Or bold it, or however you want to get it done. It's your notes for your lab. I'm just going to make sure you have everything done. And then does it stay the same? So as we get close to 90, does it still bend towards normal? As we get close to 0, does it still bend towards the normal? Alright, so that is the first part. So in the next video, we will go over the second part, procedure 2, a laser's path ray optic simulation.